Welcome Calculus AB. This is section 3.4, concavity and the second derivative test. The essential question is, how could you have used the second derivative test for the assigned problems from section 3.3? Let's begin. So, what is concavity here? I'm going to define cavity as if you have a function f that is differentiable on an open interval. The graph of f is concave upward and looks like this when f prime is increasing, so the derivative is increasing, and concave downward, which looks like this when f prime is decreasing. So where does that look graphically? Here's two examples. So we have a concave upward function, or part of one, and in this case the derivative f prime is increasing. And you can tell because we wrote a few tangent lines here. So as you start on the left, your tangent lines are negative until you get to a point that's down here, like at the vertex. And then we start creeping upward. They become a little more positive and a little bit more and a lot more positive. So the actual slope of the tangent lines is increasing. All right? Now let's do concave downward. So you're looking at this case, our derivative is decreasing, so the slope of the tangent line is decreasing. Notice here it starts as positive and becomes less positive until you get to the vertex at the top, and then it's going to start becoming more negative, and if you kept going it'd be even more negative. All right, so that's concave upward and downward. Let's compare two graphs. So this is a function, f of x is 1/3 x cubed minus x, and here's the derivative, f prime of x is x squared minus 1. Notice in this case here, we're concave downward on the left of the y-axis and concave upward on the right of the y-axis. So comparing these graphs here, the derivative, here, if this is our concave downward, notice the derivative function f prime is starting really high up here, but it's decreasing the whole time. Everywhere on the left side of the y-axis is decreasing till we get to down here at the y-axis, and then we start increasing. And when we're increasing, we have a concave upward function. Now, here's some ways to test for concavity. We're actually going to use the second derivative. So go back to that. And the rule is, if the second derivative is greater than 0 or positive, then the graph is concave upward. If the second derivative is less than 0 or negative, then it's concave downward. All right, so if we're going to apply this theorem, we're going to locate where the second derivatives are 0 or do not exist. Similar to critical numbers, but these aren't critical numbers. It's just similar. We're going to call them different points. So let's do an example of that. Determine the open intervals when the graph of this function is concave upward and downward. So we're going to have to find the second derivative to determine that, and then we got to find where that second derivative, f double prime of x, is going to equal 0 or it does not exist. So let's find the second derivative. F prime of x is going to be 6x minus 3x squared. And your double prime, your second derivative, is going to be 6 minus 6x. Okay, so the critical numbers are when this is 0 or does not exist. 6 minus 6x, it'll never not exist. It's just when this is 0. So 0 equals 6 minus 6x. And if we're going to solve for this, I'm going to divide by 6 and everything. I get 0 equals 1 minus x. So that happens when x equals positive 1. This is, think of it sort of like a critical number. So I'm going to make a chart just like we did before. Now this is our turning point on this from concave upward to downward is going to be at x equals 1. So that means the domain on the left is somewhere from negative infinity to 1. And over here it's going to be from 1 to positive infinity. So we're going to have to use some test points to figure out if it's concave upward or downward on each side. So in this case, I'm going to choose a test point. I'm going to choose x equals 0. That's pretty easy. I'll use x equals 2 over here. So let's plug those in. If I plug x equals 0, I'm going to test the second derivative. F double prime is 0 is going to be 6 minus 6 times 0, which is going to be 6. And over here on the right, f double prime of 2 is going to be 6 minus 6 times 2, which is 6 minus 12, which is negative 6. And all we're going back to that test, we want to find out when the second derivative is positive or negative. In the case on the left, we have a positive. So f prime is positive. So that means we're concave upward. So concave up, just like this. And on the right over here, that means we're at negative 6. That means my derivative, f prime, is negative. Or f double prime, excuse me, is negative. That means we are concave downward. So we have to find those intervals, and we have to, so using whenever the double prime is 0 does not exist, and check concave upward or downward. All right, so we have a concept here called the point of inflection. So that's basically what we figured out last time. It's like those critical numbers, but we call it a point of inflection. It's a point where the concavity changes. So your concave upward and downward, in this case, your point of inflection is right there. In this case, this is a cubic function. Your concavity is right here. We go from concave downward shape to a concave upward shape. And over here, we have a concave upward shape to a concave downward shape. So it's where it's changing. How do you find those points? It's where it's 0 and does not exist. So it's basically what we did the last time. It's where double prime of a number, the second derivative number, is 0 or it does not exist. All right, so let's do another example of this. Now, I've actually given you the graph right here, the answers. I just want you to see that as we do this. So to determine the points of inflection and discuss the concavity. So f of x equals x to the fourth minus 4x cubed. So I'm going to have to say the first derivative, f prime of x, is going to be 4x cubed minus 12x squared. And the second derivative, f double prime of x, is going to be 12x squared minus 24x. All right, so to find the points of inflection, we have to find where it's 0 or does not exist. So it's never going to not exist, so we have to just set this to 0. 0 equals 12x squared minus 24x. And what I'm going to do first is I'm going to divide both sides. I'm going to factor out on the right side. I can factor out a 12x. If you factor out a 12x, you're left with x minus 2. So if 0 equals that, and using a 0 product property, that means my x can equal 0 from the left one, and x can equal 2 from the right one. All right, so those are my 2 points of inflection. All right, at 0 and 2. And notice our 2 points of inflection are at 0 and 2. Now, I want to discuss the concavity. So, not looking at spoilers, let's do a chart again. So, if this first one's going to be at x equals 0, this is going to be x equals 2. And so I'm worried about my domains here. So this is going to be from negative infinity to 0. This will be from 0 to 2. And this will be 2 to infinity. And I got to find some test points in here, just like before. So I'll do a test point, x equals negative 1, x equals 1, and x equals 3. Those are easy points for me to do. So when you're testing the second derivative, so f double prime of negative 1, which if you're plugging that into this function, you get 12x squared, so you get 12 minus negative 24. So you get 12 plus 24, which is going to be 36. In the case where you plug in 1, you get 12 times 1 squared, so 12 minus 24. So f double prime of 1 equals 12 minus 24, which will be negative 12. And when you plug in 3, f double prime of 3, that's going to equal 12 times 3 squared, so 12 times 9, which is going to be 108, minus 24 times 3, which is going to be 72. Okay, and what are you going to get? 108 minus 72? Well, you're going to get 36. So in this case here, we have double prime is going to be positive, so we're concave upward. Double prime is going to be negative, so we're concave downward. And positive, so upward. And notice that makes sense. If you're looking at this graph, we're concave upward until we get to 0, and we're concave downward here. And then we're back to being concave upward. All right. So we have this concept of the second derivative test. So you can actually, instead of having to make those charts, we can test for a relative maximum minimum. So if we went back to this was a way to tell that, hey, we have a relative minimum right there. And we can do this purely with the second derivative test. So here's how you do this. Is f double prime is positive, the second derivative is positive, you are concave upward, and you have a relative minimum. Because you're making this shape here, and you're concave upward, it has to have a minimum. If the second derivative is negative, you're concave downward and you have a relative maximum. So these are at those critical numbers. You still need to find those critical numbers to get to those points. But if the second derivative is positive and negative at those critical numbers, you can figure out if you have relative max and min. You don't need to do the chart. So again, here's the theorem for the second derivative test. If you have a function where the derivative is equal to 0, so that's kind of critical numbers, except the ones that do not exist, and the second derivative of f exists, so it has to exist. Your second derivative is 0, you have a relative minimum, and second derivative is less than 0, you have a relative maximum, which I just said. Okay, so if your second derivative is equal to 0, then you can't use this test, so you must know that. So in this case, you just can't tell, so you're going to have to go back to using the first derivative test, which we did in the last section, to determine if you have a relative max or min. So let's do an example of this. I want to find the extrema of negative 3x to the fifth plus 5x cubed, and that means find the relative max and min. And I put the graph here as spoilers, but let's go over this. So to find that, I have to figure out my critical numbers first. So the critical numbers, so let's actually write this. I'm going to say my steps are find critical numbers. Find the critical numbers. So I have to find the first derivative, f prime of x equals negative 15x to the fourth plus 15x squared. All right? And critical numbers are when that equals 0 or does not exist. In this case, it's just equal to 0. So, and I'm going to factor this out. I'm going to factor out a 15x squared. So you're left with negative x squared plus 1. Okay? So what solutions for x is that going to be 0? Well, in this case, using it, this is going to happen when x equals 0 on the left. And for this one, it's going to be plus and minus 1. X equals plus and minus 1. All right, so those are my critical numbers here. And notice critical number on the graph, negative 1, 0, and 1. Now, after I found those critical numbers, I want to test. I want to do the second derivative test. Because I have to test if they are relative max, mins, or I don't know. So my second derivative test, I have to find the second derivative, f double prime of x, which is going to equal negative 60x cubed plus 30x. All right, and I have to test each of those numbers. So let's just make a little table here. I'm going to do my x, and I'm going to do x values of 0, negative 1, and positive 1, and f double prime of x. What would that equal? So the first case, when you plug it in 0, f double prime is 0. When you plug in a negative 1, this is going to be negative 1 cubed, comes out to negative 1. So you get negative 60. Wait, no, you get positive 60 minus 30, which is positive 30. And when you plug in 1, you are going to get negative 60 plus 30. Negative 60 plus 30, which will be negative 30. So in this case, when x is 0, let's do the negative 1. When x is negative 1, I'll expand this chart, and I'll do my concave. I'll do the extrema. Since in the case of negative 1, we have a positive value, this is going to be a relative minimum, as from the second derivative test. In the case of positive 1, since it's negative, it'll be a relative maximum. And again, from the second derivative test, which makes sense here, we have relative and minimum and max. Now for 0, we can't use the second derivative test. So we have to go back to the first derivative test. And this is where you're checking values on the left and right. So when x is equal to 0, what I'm going to end up doing is making a chart. And if you made your chart, you would see that you're increasing on the left and increasing on the right. So it's neither a relative minimum or a relative maximum. And that's it. I'm going to stop.